So if we neglect losses, which basically says we're assuming that all the energy supplied by the heater is being directed to change the temperature of the material, then we can use this relationship to relate the energy input as a function of the material's temperature change. And we know that this is related to the mass of the material and its specific heat. Remember, the specific heat tells us how much energy is required to change a given mass of material by a given temperature increment. This leads to the relationship we have here. On the left-hand side, we have the energy input. Remember, this has units of watts or energy per time. We multiply that by a time increment. That gives us units of joules or energy. And on the right-hand side, we have the material's mass times the specific heat, which has units of energy per mass per temperature, times the temperature change. Here, the temperature and the mass cancel, so we have units of energy or joules on both sides of this relationship. Now, we can use this in conjunction with the second experiment that was performed, which is the one where the heater was activated for 100 seconds. And then after that time, a long time elapses, and then the final temperature that was measured after that long time was 39.8 degrees. So when we apply that, we see that we have all these quantities. We've applied 20 watts for 100 seconds. This is how many joules of energy that was input. And again, we're assuming that all of that goes to change the material's temperature. We know the mass of the material. So remember, there's two samples, each of which has a mass of 78 grams. And the temperature change at steady state after this energy was input is the long time temperature that was measured, 39.8 degrees, minus the initial temperature, which was given to be 23 degrees C. So we can solve this for the specific heat.